Hello, this is Dr. Vev. In this final video on energy, let us investigate a very important system known as the spring mass system using energy. Now, the starting point for an energy approach is to see if energy is conserved. So we have to show that the non-conservative work in the system is zero. Let us see what all the forces are on the system. There's a normal force acting here, but the normal force is perpendicular to displacement. The displacement is occurring in the x direction only. So there's no work because of the cosine 90 factor. We are going to assume there's no air resistance. There's no friction. And the one other force that is acting on the block and the spring together is this normal force F sub n, which could be either acting away from or towards the spring depending on how the system is oscillating. Well, that normal force we're going to assume acts over no distance. In other words, the spring is not pushing in or out of the wall. So for those reasons, the non-conservative work is zero. So total energy is in fact conserved. The total energy is the sum of the kinetic and the potential. The kinetic energy is 1/2 mvx squared and the potential is 1/2 kx squared. So that's the total energy of the spring mass system. What we have to now do is use the conservation of energy somehow. That can be used as follows. If energy is conserved, the rate of change of energy with time must be zero. So let's see what happens when you differentiate that equation. Now this is a very common approach known as the energy method. So I'm going to get 0 equals, when I have derivative of v squared, I'm going to get 2 up front times vx times the derivative of vx with respect to time. And then I do the same thing over here. When I differentiate with respect to x squared with respect to time, I'm going to get a 2 there. 1/2 k x times dx by dt using the chain rule. But dx by dt is just the x velocity, and dv by dt is the x acceleration. These two's cancel with 1/2. So I'm going to end up getting 0. I'm going to get m times a times vx, so I can take vx common. And here I'm going to get k times x times vx. So I've already taken that vx common, so I'll write it as kx equals 0. Now this is an equation which is a product of two expressions and it's equal to 0. So we know that either vx must be 0. That is known as a trivial solution, because under this condition Vx equal to 0 means the mass is not moving. The energy is still conserved. It's just that it's 0 plus 0. So it's a trivial solution. It's not very interesting. The other solution is far more interesting. That tells us that max plus kx equal to 0. We will revisit this in week 10. It's known as simple harmonic oscillation. But right now we just want to recast it in the form of Newton's law. Newton's law says the force of the spring must be equal to, which is equal to negative kx, is equal to mass times acceleration. And so you see that the Newton's second law is correctly reproduced by the energy method. So in this little exercise, it's done mainly to show that this works, and now we'll go to the more difficult case of the vertical spring in which gravity also comes in. I just want to point out that the energy diagram for this particular problem looks as follows. If you're plotting here the potential energy, it's going to look up like a parabola. X is the displacement from the equilibrium. So the equilibrium is somewhere here, and there's positive x this way and negative x that way. And both positive and negative are allowed on either side of the equilibrium. The total energy is E0, which is somewhere here. And the total energy is the sum of the potential and the kinetic energy, which means that at any given time the kinetic energy can be got by looking at how much is left over from the total energy up to the potential energy. So that this arrow goes from 0 all the way to a maximum value, all the way back to 0. So the particle oscillates with the maximum kinetic energy at the equilibrium point, and then at these 2 points, known as the turning points, it has 0 kinetic energy. They're called turning points because the motion turns around from negative to positive, positive to negative at those points. We call this negative xm and positive xm. So those are the features for horizontal oscillation. For vertical oscillation, some things change. For one thing, gravity is in the picture. So let's look at the vertical case. Let me draw a quick diagram first. The spring is now suspended from a support stand or ceiling of some kind. I'm going to introduce some variables. When the spring is hanging without any oscillations, if it's not moving up and down, if it's just hanging there, I'm going to call that the equilibrium distance, y sub e. And the spring is going to get stretched from its unstretched length. So this unstretched length, which I'll call y naught, and the amount of stretch from y naught will be called the total stretch of the spring, because the total stretch of the spring is from the unstretched length. So that is y, the variable y, and then the spring goes up and down with some speed vy. Gravity is acting downward. Let us write the energy for this system, just as we did for the previous one. So in this case, the total energy E naught will be the sum of the kinetic plus the spring potential plus the gravity UG. Now I'm going to measure gravity from here. So the gravity for the support is 0, so everything below is going to be negative. So let's write down what this is. This is E naught equals 1/2 mvy squared. The spring energy is 1/2 k y squared, and the gravitational potential energy is negative mg y plus y naught, because y naught is the unstretched length of the spring, and the additional stretch of y brings the total length of the spring to y plus y naught. Okay, so that's what we have. Observe that mg y naught is just a constant, so it really doesn't affect anything in this motion, but we can see that readily enough by simply differentiating both sides. So we're going to similarly, just as we did for the previous problem, the line of attack for this problem is exactly identical. We're going to differentiate both sides with respect to time. And set it equal to 0. So I'm going to get the 2 cancels out in the same way as before. So I have Vy in common. I'm going straight to that step. May plus ky. And here I would have got mg times dy by dt, which is v sub y, which I've already pulled out. So that's going to just be negative mg. And as I already mentioned, mg y naught when differentiated will give me 0 because it's not time dependent. So that's equal to 0. Once again, you have the trivial solution where the mass just hangs, nothing interesting. So we'll take the non-trivial solution, and that solution is may plus ky minus mg equal to 0. So by the way, you can recast this to make sure this comes out to be Newton's second law. What I'll write is, I'll write it as may equals mg minus ky. And that's exactly Newton's second law, because that's the force of gravity plus the force of the spring. Recall that the force of the spring has got a negative sign according to Hooke's law. So this also reproduces the Newton's second law, what we expect. So the energy method gives us the same data as Newton's second law. Now let's do a few more things because I have some time left. So how about we check what happens if AY equal to 0. AY equal to 0 is the condition for equilibrium. It's exactly what I earlier said was a trivial solution. Nothing happens. So for AY equal to 0, I'm going to get mg equals, because this is 0, the right hand side must also be 0. So I get mg equals ky equilibrium. So this is a good way of determining ky equilibrium. The equilibrium distance is just mg upon k. Now I would like to draw an energy diagram similar to that. Before I do that, I have to somehow make this look like a function I can actually plot. So what I'm going to do now is write the total energy once again and see if I can do this in a way that would make it apparent what the graph should be. So the total energy E naught is going to be 1/2 mvy squared. And then here what I'll do is I'll try to complete the square. So I'm going to take 1/2 k outside. Then I get y squared minus 2mg over ky. So I'm just focusing on the 1/2 ky squared term and the negative mgy term. Those two terms can be written like that. And then I'll add and subtract the x squared plus b. This is a squared plus 2ab plus b squared. So I'm going to add and subtract b squared, which is mg over k squared minus mg over k squared. This is what you studied in earlier classes as the process of completing the square. And then I'm still left with this term mgy naught, which is just a constant energy term. So let us look at this a little bit more. So I'm going to get 1/2 mvy squared plus 1/2 k. Well, the completion of the square is y minus mg upon k, but mg upon k is precisely y equilibrium. So y minus y equilibrium squared, and then I have to deal with 1/2 k multiplied with that, so that gives me negative 1/2 m squared g squared upon k, and then you still have this minus mgy naught term outside. All right, so apart from a constant, that's the energy, you'll notice that this is very similar to the simple harmonic oscillator. So let's actually take the trouble of plotting it. Now when I see an expression like this, I get a little bit worried that the units are maybe not working out. So what I always like to do is make a quick reassuring check for myself. The force, mg is a force, so that's Newton squared. Spring constant is newtons per meter. So that's going to be newtons times meter, and newton times meter is the same as joules. So that reassures me. Next, we shall plot this graph. Yes, there's a constant. So what I'm going to do is I'm going to redefine my variables. I'll call this a new energy, E naught prime, as E naught plus all these constant terms, plus 1/2 m squared g squared by k plus mgy naught. And then that E naught prime is just equal to 1/2 mvy squared plus 1/2 k y minus y equilibrium squared. So I'm going to plot with respect to constant E naught primes. Let's finish the plot. The big difference is that y equal to 0 is not as important as y equal to y equilibrium. And then the plot occurs on either side of that. Now if you plot it with respect to E naught, it will all be shifted down because of that negative sign. But since I've plotted with respect to E naught prime, it will be exactly at the at that position. And here you have the turning points. The turning points are going to be YE plus YM and YE minus YM. Right? So that's going to be our general nature of the graph, and the kinetic energy at any given time is the difference between the two. So the bottom line is gravity does not play a big role in this oscillation at all. It is still governed by the spring constant and the mass, and gravity is just a shifting of the total energy.